All right, y'all. What's going on today? Welcome to my channel. My name is Ryan. This is my YouTube analytics spot right here on YouTube. Today, I want to take a look at how we can predict power outages and the associated financial losses based on those power outages based on extreme weather events. So, we're going to look at a couple different things. Potential lightning strikes, things like severe gusts of wind, very high wind, can topple trees, take out power lines. Lots of rain, right? Especially if you have a hurricane and wind, that's a deadly combination. Those can topple trees and cause a lot of damage. So I actually had a job a few years ago where I was doing this exact same thing. I was working for an energy company and they wanted me to predict power outages and then how much that is going to cost, right? And they want to do things like tree trimming, it was called, so they can preempt the power outage and trim the trees before they fall down during the storm. So I was promised that we had all the data we needed to do the analysis. In reality, we had probably like 5% of the data. Most of it just did not exist. So that was unfortunate. And the whole analysis kind of was extremely short in its duration because we just didn't have what we needed. But I thought it was an interesting challenge anyway, and I finally had some free time, so I thought I would circle back here and try to answer this question, right? So I wanted to try to predict power outages, looking at storm trackers, vegetation proximity, and overall like different types of weather dynamics. Again, like I said, either severe wind gusts or lightning strikes or intense rainfall. And I think really this can add a lot of value to any kind of energy company and even like local governments to try to coerce people to act responsibly, especially in intense um, weather events in regions prone to hurricanes. You get this a lot down south in Florida, Mississippi, Louisiana. They had a bad one. I think Hurricane Katrina. We had a bad storm in New York City, Hurricane Sandy, many years ago. So these things are really devastating, right? And if you really prepare yourself, you can leave the area in the general vicinity where there is going to be severe weather conditions, right? And just get the heck out of there. And we can do things like tree trimming or try to intervene somehow if you're the energy company or a government entity and just try to protect people, right? Like people sometimes just need the heads up. They need like a big brother oversight, right, for how to act and how to prepare for these types of events. Okay, so I think that's enough setup. And of course, we're going to look at economic implications. What kind of financial consequences are there when there's an extreme weather event that makes landfall. Okay, so I think that's enough. So I want to go ahead and download some basic data in and around New York City. So I'm going to get New York City and the 5 boroughs that include New York City. That is all of New York City, right? Manhattan is off by itself. That's one of the boroughs. There's also Queens, Brooklyn, Bronx, and Staten Island, right? So I'm going to look at New York as my focal point right here. I'm going to get OpenStreetMap data and download this. So there's a couple of APIs I can hit. Overpass API. There's an interpreter. There's another system called Kumi, and there's Z Overpass API interpreter, which helps combine all of this information. They give you very useful features like latitude, longitude coordinates, and all kinds of things relevant to that. So we're going to see all that in just a minute here. So I'm going to go ahead and create some rows, and in that list, I'm going to append OM or OSMID, power, name, and geometry. So again, these are the geometric coordinates, and you can see that these come to us in the form of they're called what is it? Geometrically configured lines, right? Where you look at polygons. Like polygon would be one type of geometry that we look at, and basically they show the borders of different territories. So it can be the border of a zip code. It could be the border of a what is it called? FIPS area. I forgot the name. County, like county codes, right? You have FIPS data. You have latitude, longitude data, and zip code data too, which shows like the approximate boundaries or the polygon shapes of these different territories, right? Where one zip code ends, another one begins, or when one county inside of a state ends and where another one begins. So it's very helpful for that kind of thing, right? So we're going to send a block request to go ahead and get this information. This is going to give us grid segments. It's called GPKG, and the files are downloaded to my to the base not login, base install for my Anaconda prompt. So everything goes to users, Ryan underscore, and everything is just saved there, right? So that's where you look for it. If you look for your own, these are the 5 boroughs that I just described. So Manhattan, Brooklyn, Queens, Bronx, and Staten Island. I just want to focus on these 5. If you have another region you want to look at, something in North Carolina, something in, I don't know, Virginia, or down south, of course, Florida is very prone to hurricanes. I think that's called Hurricane Alley. Louisiana and South Carolina, North Carolina, right? Like these are big hurricane hotspots, right? So if you want to pick your own region of the country to analyze, that's fine. You just have to predefine it. I'm looking at New York City. That's where I live. Now, I know there's not tons and tons of hurricanes, but we still get them too, right? We had Hurricane Sandy back in whatever that was, maybe 2013, 2014-ish. You could Google it and find out. That was a pretty bad one, but New York isn't prone to too many hurricanes because by the time the storm gets this far north, it's kind of dispersed or it's weakened. That is the rule, but there's always exceptions to every rule, right? So there are some pretty nasty hurricanes that come through here once in a while. But the point is, if you want to name your own geographical region, just pick your own and you can focus on that, okay? So I'm going to let this code run. It is going to give me the grid segments GPKG and download this from the website I described before. So this is pretty useful for getting all kinds of data about geographical coordinates, again, longitude, different polygons, different shapes of geographical regions, and we can go ahead and assemble that together and understand what the layout of the region looks like, understand what kind of weather event or weather impact we can expect here, and then what the overall outcome or the consequences is going to be for that event, including the financial impact as well, okay? So I just did the download, so it went right here. I'm going to go ahead and open that file that was just downloaded so I can go ahead and interpret that. I'm going to be pulling out things like segment ID, feeder ID, and then geometry, okay? And again, you'll see what this data looks like in just a second. So here's the file that I downloaded from the API fetch, right? So we have the line strings. These are the geometric coordinates down here, and then we have some information about OS, MID, power, name, and then geometry would be the last column over here, okay? So if I scroll down just a little bit more, we can start to see how this is assembled down here. So again, I'm getting all these features into my data frame. I have the event ID, the time, longitude, latitude, wind gusts. So that's how severe the wind is in terms of miles per hour, precipitation, and then lightning count. Okay, so these are the 3 big ones I'm looking at. If you wanted to add different types of events for natural disasters, I could think of maybe things like landslide, what else? Maybe tsunami, volcano. Like in New York City, we don't have these things, so I'm not going to analyze volcano eruptions, right? But I think these are relevant: wind gust, precipitation, and lightning, and all 3 can be quite devastating too, right? So we'll see evidence of that in just a minute. So we have the time, lat long, wind gusts. This is in miles per hour, so this is pretty mild over here. Some of these get a little choppy, up to 25 miles an hour. So that's getting up there, but still not like hurricane force wind. This is pretty mild actually. Precipitation, lightning count. So we see 43 here. That's kind of intense. 43 again. So that might be a little bit of a concern. Down here we see 7, 2, 3, not a big deal. And then we see the geometrical points right there too. So let's try to break this part a little bit more. We have the event ID, lat long, precipitation, lightning count. Control Enter to run. Okay, and I downloaded this. Now this file is, like I'll be honest, this one is a little bit more optional. You don't absolutely need this if you are doing this type of analysis frequently and you didn't want to keep on fetching the data and saving it down, I would recommend just doing a fetch once, save it down. If you're going to be analyzing the data over and over, I'm just going to look at this once, so I'm just going to fetch it. You can just store it in memory in the data frame or in the list and convert that to a data frame, or you can save down the file if you're going to be working with this multiple times in one day or multiple days over the course of a week or multiple weeks. Then you probably want to save it so you don't have to go fetch it all the time. But again, this is kind of an optional step. It's really up to you if you need to do this or not. Okay, so moving on here, we have more of a breakdown of the data. We have storm times, and we're also looking at segments of counts of lightning strikes, right? And then wind gust 2. So I'm joining all of that together and trying to understand what is the most serious conditions that we need to be aware of here. So we have the ID. These are different segments located around New York City. We're looking at max wind gust. So that's getting up there a little bit. These are kind of high right here. Again, not super concerned about these. But again, I do want to know the maximum gusts to know, is this going to be serious, like, 50, 60 miles an hour? That's getting up there. 80, 90, that's probably hurricane force winds. 25 is nothing to be too concerned about. It's not nothing, but it's really not something either, okay? Lightning strikes, so 35, 33, it's kind of getting up there. Again, this could be a cause for concern. We'll see a little bit later how that plays out, and we see the maximum precipitation. This is in terms of inches. So 9 inches in one storm, that's a lot of precipitation, okay? So that's something that we want to be aware of too. And then we have the date. So today is Halloween. It's October 31st, 2025. So we have today's date, right? We have some other information about the weather conditions. So let's move on here to continue with this analysis. And this part runs a little bit slow, so I'm probably going to hit the pause button here. Actually, it wasn't too slow. That was pretty fast. Well, I worked on that code a little bit yesterday. That was pretty slow yesterday morning. I did refactor it a couple times, so I guess it's a little bit more performant now. So in this case, now we're getting distances in terms of number of trees or density of foliage. So like I said, when I was commissioned to do this for the energy company, they wanted to see how tightly packed the trees were together. They didn't have this data per se. I mean, they had very, very primitive, rudimentary data. They didn't have any great data. But I did what I could for these guys. But this was a concern, like how close are the trees to each other? Okay, is the vegetation pretty densely packed in there? Because if a big storm blows through, it could knock down a whole bunch of trees, especially if there's a lot of rain with that wind. Okay, the ground gets soggy, soaks up the water like a sponge. You have a big gust of wind, and it can knock over a whole bunch of trees that wouldn't fall if there was wind only, right? But when you mix wind and rain together, that becomes a deadly combination, right? So we're looking at distances between trees to understand density of foliage. We're going to look at the counts of trees, the segments or the distances from different trees in the forest. Are they close together? Are they far apart? If you're more in the beach area where there's low-lying trees, the trees are probably shorter than the average person, and it's mostly shrubs or bushes, there's no trees to fall down, right? Like, you don't have to go trim trees at the beach because there's no trees there. You really want to focus more on the mountains. What else? Like corridors. They were called corridors at this company. Is this an interstate highway with a lot of foliage hanging over the edge of the street? Is this like more of a residential neighborhood, more suburbs? Is this more of an urban environment, right? So you have to kind of know the area and know the density of the foliage there, and then understand, does it make sense to go trim those trees, or are there basically no trees to trim and you can just avoid the whole area, right? So trees per kilometer, we are counting those trees again to determine the intensity of the trees or the density of the trees. We're getting counts and densities down here. Okay, and moving down, we have the segment, the number of trees. We are joining these together. So we have the GPD data. Okay, this is the data I just downloaded. The GPD data, not GDP, that's economics. And we're merging this with segments. So we want to know the nearest trees in the data frame, or there are a lot of trees here that potentially could fall and cause an issue, and what kind of segments are we working in, and what's the density? Is it more like 100 trees per square kilometer? Is it a couple hundred trees? Is it going to be more? Is it going to be less? Things like that, right? So we're creating these data frames and merging them together, and we have these segments of the foliage right here. So I think I just ran this. Let me run this together. Again, this is going a little bit faster now, so I'm comfortable running this. Okay, so now it is running slow. So yesterday I thought it was running a little bit slower. I just hit it before I started the whole spiel here, and it seemed like it was going pretty quick, but now maybe it is slowing down again, and that's fine. So I will go ahead and pause the video at this point. You don't need to sit here and wait for this thing. I'll wait for it to finish off, and I'll restart when this thing is done, okay? Okay, this is finished off at this point. So I think we are in a good spot. We have the segment ID. I'm not super concerned about that. That would be more like maybe nice to have, but we have geometry, so I don't know if we need the segment ID too much. We have geometry line strings. Remember, these are like polygons, so it shows the shape and sort of like the outline of different counties or different zip codes, depending on what we're looking at here. So we have the tree density, that's important, and tree density like at 100 trees per square kilometer, or are we more like 200 trees per square kilometer, right? So that would be much denser, and that might require more attention. If it's only 100 spread out around 1 kilometer, it's probably not too dense of a foliage area, and not a lot for for us to do there. Okay, so I think this looks good. Let's go to the next step here. So we are going to go ahead and do another merge with another kind of data set. So we're looking again at tree densities, minimum densities. We're going to join this together on another pre-existing data set, and then we're going to loop through all the items in this list right here to fill in any defaults. Okay, so if we have missing data, we shouldn't have a whole lot, because this data set that I showed you before should be pretty comprehensive, and I believe, like, I'm not an expert in this area, but I believe that they maintain these things pretty well. So we shouldn't have too many missing values, but with some of these algorithms, when you're doing your testing, you really can't have any missing values whatsoever, or the algorithm isn't going to work. So just to as a fail-safe to prevent that from happening, I'm going to go ahead and fill in any potentially missing values. I don't think there's any, but just to make sure. Okay, so and that by the way is done just for to have a comprehensive data set. If we did have a few fields or rows or whatever that had some missing values, we could just kick those out. We could just ignore those, just delete those or something like that. But you don't really want a lot of missing data points in your data set if you're going to make a like some kind of comprehensive analysis, right? Or you want to use some type of interpolation to go ahead and fill in those data points, either forward fill, backfill, or something to that effect, to get all the data points filled in, just so you don't have to deal with missing values. Okay, so my computer just crashed all of a sudden, no reason whatsoever. But I believe we were about here. I'm going to try to append the second video file after the end of the first, and hopefully that works out. We'll see how that goes. So we have the nearest data frame and the segments data frame, right? So we're combining all of this data together. So we have the segment ID, the geometry coordinates, tree density per 100 meters, per 200 meters, and distance, minimum distance between trees. Okay, so that tells us how dense the foliage is or how non-dense it is. Again, we have wind and lightning. So these are the three types of events we're looking at. There's other types of weather conditions. Okay, so you can bake that into your analysis if you need to do that. In New York City, we don't get lots and lots of these other things, so I'm not looking too closely at that right now. So we have the rules over here: lightning, number of lightning strikes, right? So I want to know if it's going to be high, low, something in between. Is there going to be a lot of rain? And then the density of the foliage, right? And then the gusts of the wind. So these three things together can be pretty devastating Um, so that's what we're trying to figure out. And we have to define whether or not a power outage event will occur. So that's really the dependent variable. That's what we're trying to predict here. In every type of machine learning scenario, you always need a dependent variable, right? So I've said this many times, at least several hundred times in my other ML videos. You have the independent variables, which is everything that you're looking at minus IDs, because you never look at an ID. You don't try to predict an ID. That's just an identifier. That's it, minus the target variable, okay? So you strip these out, and the target variable is what we're trying to make the prediction on, or it's called the dependent variable, right? So these can be the independent variables, okay? And all of those can have an impact on the power outage. So the power outage can be dependent on maximum gust of wind, sum of lightning strikes, maximum precipitation, the time of the day. That can be an independent variable. Sometimes it is, sometimes it's not. I'm saying in this case it is. Tree density 100 and 200 meters, and distance between the trees. So given all that, we're trying to predict the power outage. Okay, so down here is our ML model. We're going to use an XGB classifier. So a classification model tries to predict a label, and it's usually binary, so yes or no, power outage or not power outage, true or false, on or off. There's going to be some kind of binary outcome. It can't be both, it has to be one or the other. So we have the training and testing. These are the independent variables right here. This is the independent X train, X test, and these are the dependent training and testing. So like I said before in many of my other videos, the training is essentially like a middle schooler or a high schooler or a college student going to class. So you get the training, that's going to classes, doing the homework, interacting with the professor, talking with the students. That's all the training. The testing is when you sit your butt down in a chair and you take the test. And how you perform the test is a gauge of how well you've learned the material, right? So that's true of a student, it's true of a machine learning model. If the ML model can learn the material pretty well and make accurate predictions into the future on unseen data, right, and generalize what it's learned, not memorize, but generalize what's learned, then the model is performing well, right? We picked a good one. If not, then we have to figure out why. So I set up doing the training and testing down here. It looks like an issue. This is weird because it's just worked right before. Let me try this again. Control Enter. Sometimes you run these things twice and it doesn't work. You run it once, it works fine. So yeah, I was looking for something that didn't exist, just a column. The column name probably got overwritten. So like sometimes I try to build these things bulletproof so it can't fail. Sometimes you run it and you expect to run it once and you're done, one and done, right? So this is a one and done. If you try to do it again, it's probably not going to work. It's going to get overwritten. That's fine. It's just that's the way it's designed. And my intention is not to make this thing bulletproof, but to analyze, the financial loss here from power outages and what kind of consequence that's going to have. So we have everything all set up here. We have the risk, right? Here's the risk identifier right here, or the probability of the risk. Is this high risk? Is this low risk? Expected cost in terms of US dollars, maximum wind gust, lightning strikes, precipitation, tree density, so on and so forth. And then the geometry, that's how we're going to do the plot. So the next step here is to plot everything on a Folium map. A Folium map is a great way to visualize some type of geographical or geological layout, right? We're looking at the mean streets of New York City in this case. So the 5 boroughs of New York City, I want to see what that looks like plotted on a map, and I want to see what the weather impact and the financial impact for this weather event in this neighborhood. So I take everything, load it into Folium maps, okay, and it basically takes different layers and it bakes in different layers and integrates different parts of the map and coalesces everything or collates everything together, whatever you want to call it, and then comes up with the final display. This is called M. M is short for map. This is a pretty standard way of doing it. And lo and behold, we have our map. So this is Brooklyn. If I zoom out, this should be very apparent right here, or this could be the edge of Brooklyn and maybe Queens, because this is about where it ends. Queens is actually, JFK is actually in Queens. It kind of looks like Brooklyn, but Brooklyn kind of cuts down a little bit. This might actually be in Queens. It might be right on the border. I think it is. I think it's actually Queens where the power outage occurs, and it comes from a lightning strike, right? So if you look close over here, you'll see the risk is about 50-50 chance, 0.50. There are some gusts of wind. It's not going to be horrible. 25 miles an hour. That's not like life threatening right there, but it's a little gusty. It's a little breezy out there. But the big concern here is lightning strikes. We're going to have 35 lightning strikes, and the estimated cost here is going to be about $2,008 in terms of damages along this street. And looks like Queens to me. This looks like this is probably Queens or right in the edge of Brooklyn. And it looks like it probably took out the transformer above. Out here, all the power lines are above ground. Where I live, there's some above, some underground. In New York City, it's all underground. They put it underground, right, to protect the city from big storms, so we don't have 8 million people going without power. If there's a problem, right, it's pretty well protected underground. But out here, you're pretty far out in Queens, and this is above ground. So I'm guessing a transformer came down, put the mouse over the line here. The lightning strike is a 50-50 chance. The segment is the ID. This is where this is occurring. We have this plotted on the map, so we don't necessarily need the segment at this point, but it's nice to have. 35 lightning strikes, and the expected total financial damage is $2,008. We can actually modify this map to make it slightly look a little bit different. So this is kind of the gray map. This is the toner. It's not super useful. This is a light map where everything is kind of like bleached, I guess. I think this is probably the most useful view right here. And we can see, okay, so there's Brooklyn. Queens kind of like swings down on the side. You can see JFK, that is in Queens. So I'm guessing this is probably right on the edge of Queens, or Brooklyn, probably Queens. I'm going to go with Queens. Okay, and I see other Queens, and that is pretty much it. We only have one lightning strike expected to come up. This is, what was the date? This is actually Halloween 2025, and that is 10/31. That's the date today, so 10/31. Potential lightning strike out on the edge of Queens. And if this event does occur, it's like 50-50 chance. We saw that. We saw the risk potential was about 50%. It's going to cause about $2,008 in damage if this event occurs. Okay, so the risk 50%, gust of wind. That's kind of a threat. It's not huge. Lightning, 35 lightning strikes predicted, and the total cost is $2,008. That's it, guys. So that is how to predict power outages and the associated financial losses based on extreme weather events. That's my take on it. So there it is with all the data put out right in front of you, right in front of your very own eyes. Now, if I worked for this energy company today, I would just take ownership of this thing and just say, listen, if you can't come up with the data, let me do that for you. Okay, they didn't have the data, they didn't have hardly anything. I think 5% of what we needed. That was unfortunate, but look, where there's a will, there's a way. Okay, sometimes you have to go above and beyond. If you can't get what you want, just talking to the normal stakeholders and the powers that be, you have to kind of like go over their heads, right? Sometimes people say you have to deal with the deck that you were dealt, right? You deal with the deck you were dealt. I was dealt a deck of 5% data. I was promised 100%. I couldn't deal with it then. Now I could do it. Okay, I'm a little bit more mature, more innovative now, a little bit more tenacious now than I was a couple of years ago. So now I can execute on that. But sometimes you are dealing with a deck that is not stacked in your favor, right? And you have to figure it out. You have to go above and beyond and figure out how to deliver what needs to be done, right? You got to do that, guys. You got to do that. So if other people come up short, that's fine. You don't come up short, you come through. That's what you have to do. You have to come through. So that's just a lesson in how to, be diligent, be thorough, be tenacious, and just deliver to meet those expectations. So that's it, guys. I'm going to wrap it up here. Thanks for your time. I'm going to post a video later today, and I'll see you when I drop the next video, which should be a little bit maybe later today or early tomorrow. Okay, so keep an eye out for that. Thank you so much, and I'll talk to you soon. Goodbye.